Hi everyone. I am Anuj Kumar, working as a Prime Minister Research Fellow at IIT Roorkee, and this is the basically revision session of this NPTEL course, Colloids and Surfaces. In this particular session, I will be discussing some basic formulas for your revision, and after that, I will be solving rapidly the problem we have discussed in the previous some of the previous sessions. Okay, so these are the commonly used formulas. Okay, the first formulas you have to see with the specific surface area. Okay, and the surface charge density and the grafting density. So, the specific surface area is basically meter square per kg or this one, and the surface charge density you can say the total surface charge divided by the area, and total surface charge you can calculate the charge, that is q, multiply by number of dissociated functional groups and divide by area. Simple calculation. And grafting density is basically the number of molecules that is adsorbed on the particle surface, okay, per area. And the Brownian motion, you already deal with this formula, that is the mean square displacement, where d is the dimension and this t is the diffusion coefficient and t is the time. Okay, and you have solved similar problems in for like Perrin's experiment. Okay, and this is the another important equation, that is Stokes Einstein equation, that basically used for calculating the diffusion coefficient, and it relates between the thermal energy and divide by this term where r is the radius of the particle. Okay, and mu is the viscosity. And the the next used formulas. Okay, let me see some. Okay, these are the different types of forces. First one is the hydrodynamic force, that is Fh is denoted by this 6 pi eta m a v. A v is the velocity and a is the radius of the particle. Similarly, the Brownian force and the force of gravity, okay, simply this is mg, and you can expand it, the mass is equal to density into uh, volume, and these things is already done here. Okay, these are basically the uh, subscript. This is the rho p minus rho m. Okay, and similarly the osmotic pressure. Okay, and finally the Jonas potential. Basically, it describes the two terms. First is the repulsive part. Second one is the attractive part. Okay, a simple formula. And in the DLS experiment, dynamic light scattering experiment, you have dealt with this autocorrelation function G2 tau, and it is the relation between there are two correlation function you can more read in the your theory sections. So this is also a autocorrelation function. This is basically the relation you can write with directly, and this is the intensity changes with respect to time. This is the short interval of time, that is tau. Okay, and the final relation you will get like this, and s is the scattering vector. Okay, so these are the formulas only for your revisions. Okay, uh, on fundamental things on, or you, how you are getting these formulas, you can go to the theory part and see into the details. Okay, next is the van der Waal interactions. You have Under the van der Waals interaction, you have deal with these three terms, that is the Debye interaction, Keesum interaction, and the London interaction. Or it is basically take place. Debye interaction will take place when there is a one molecule is having a permanent dipole moment, and other one is having the induced dipole moment. And similarly for Kisham interactions, if you are having a permanent dipole in both the particles, they are interacting, so it will be categorized as the Kisham interactions. And similarly, if both the particles are uh, uh, under the induced dipole, so they will follow the London interaction term. Okay, so we can easily write the van der Waals interaction is the sum of these three terms. Okay, that is the van der Waals interaction is equal to the Debye terms and the Keesum terms and the London terms. Okay, so this is the formula we got finally. Okay, this minus sign can be cancelled out, and after this formula, you can easily calculate the fraction. Okay, total fraction. That is a KD divided by this beta 1 terms, and you can easily calculate the Debye interactions. Okay, this is fine. So I have solved similar problems in the previous sessions, so you can see those videos. Okay, I'm just rapidly discussing the basic formula. After that, I will discuss some problems related to these formulas. Okay, so I am giving the basic ideas, so that you can revise those formulas very quickly. Okay, and this is the Hamaker constant, the combining relation, or you can say the solvent effect. Okay, so there are two cases. If you are having this one, okay, if I denote this first phase as 2, and the solvent as 1. Okay, and you are basically you are dealing with here, dealing the reaction engineering approach. Okay, if these two, one dispersed phase is here, one solvent is here, and after how they interact, the you can deal with the final products. Okay, so resultant Hamaker constant you can get, how you can get, that is first is the A2, A11, sorry, this is A11 plus product minus reactant minus A21 or A12 or minus A12. These will be minus 2A12. Okay, and this A212 will be A11. These are the similar terms, and this term is expanded basically on the geometrical mixing rule. Okay, you can write here the A12 is equal to A11 into A22. So this formula you can write like this, because A minus B square, if you expand this expression, you will get this term. Okay, so this will be the resultant Hamaker constant for this particular arrangements. Similarly, if you are having these arrangement, if one is the solvent and these are the, you say, the particles, different types of particles here, and this one is the solvent, and similarly you can solve for the uh, this particular arrangement. You can solve, this one is the solvent and 3 2 are the particles. Okay, after that what you can do is, okay, so what you can do is you can expand the formula, that is 24 pi d naught square gamma. Okay, you can write in the form of that particular, and you can expand this expression, and finally you will get in the terms of the surface tension. Okay, Here are uh, the values for different geometries. Okay, you will deal, and these are the details of this. These details of these symbols. Okay, you can basically see in the theory what is the resultant expression for that. So you should remember that. Okay, and the next important thing in this particular course, that is different models or to explain the electrical double layer. First is the capacitor model of electrical double layer. What it says. Or okay, so if you are interested, or if you want to calculate the electric field strength, that is E epsilon, so you will get this term. Okay, and further expanding it, this is the basically del psi is the potential drop. This drop is del psi. Okay, and this delta is the uh, uh, electrical double layer thickness. Okay, so finally you will get this expression. Sigma star is the surface charge density. Okay, surface charge density. And second is the Poisson equation. You are already familiar with, that is the del square psi is equal to minus rho star by E. This is also the charge density, but for one dimension you can write this as similarly like this. Okay, for three dimension you can write the y term and the z term. Okay, another one is the Boltzmann factor. Okay, uh, and similarly the Poisson Boltzmann equation you will get in theory section. You have already derived these expressions in detail. Okay, so the potential distribution near planar surfaces, you will deal with the Debye-Huckel approximation or linearized polymer Poisson-Boltzmann equation. Sorry. So this equation is a very important equation, and more problems will be solved out by using this simple formula. But its limitation is it is valid for the low potential. Okay, that is the Z E psi should be less than kBt. This is Kp Boltzmann constant T. Okay, and the linearized Poisson-Boltzmann equation is applicable in the case of low potential. I have already indicated, and the approximate magnitude of potential at this room temperature for monovalent ions that satisfies the low potential can be obtained from this expression. Okay, so if you have to define the whether the potential is the great potential or the lesser more potential or lesser, you can basically say with respect to this 25.7 millivolt value. Okay, so next, this particular expression, if I write this term is equal to kappa. Okay, so this will be the kappa square psi. Okay, and if uh, these conditions are there, you can use this formula for calculating this the potential value. Okay, you can put the value of separation distance here. Okay, I have already solved multiple problems on this formula. And another important expression for is for Debye-Huckel approximation. That is the same, the potential this potential expression, and this particular expression is for spherical particles. You know, where Rs is the radius of the spherical particles. Another important parameter is the kappa. I have already indicated. Okay, so kappa square is equal to E square, that is the charge on electron. Epsilon is the basically the permittivity. You can expand it like this. This is the vacuum, and this is the relative permittivity of the medium. Okay, and this the at infinity the number. number density, that is the number of molecules per meter cube, you can calculate by simply using the formula, that is the n infinity is equal to 1000 into molar concentration or into multiply by Avogadro number. Okay, like this. Okay, so you can write this formula here and you will get this final value. Okay. Okay. Again, here is a comparison between capacitor model and the diffuse double layer model. Okay, and you will get the similar expression as you got for the capacitor model, but you have to replace the psi naught by this potential drop and K inverse replacing this double layer thickness. So basically, this is the, you can treat the kappa inverse as a double layer thickness, or you can say it as a D-base screening length. I will discuss later on. So another terminology, that is potential distribution, we will talk about the near planar surfaces. That is the Goey-Chapman theory. For large value of separation distance at which the potential has fallen to a small value, which is independent of its initial potential, that is psi. Okay, so here you will replace the psi term by these gamma terms. Okay, and here is the expression for those, and you will get finally this expression. Okay, so this is the limitations for applying this formula. And the special case, another special case, that is if you are having the large value of x and large value of initial potential. Okay, so in this case you will getting this value equal to 1 based on the experimental results. This term is considered as 1, so this term will become this, and you can easily manipulate the formula or rearrange the formula, you will get the final answer for potential. Okay, I have already indicated you can denote the K inverse, okay, as a debase screening lath or double layer thickness. Basically, this is the structure of electrical double layer, and you can apply this formula for calculating the kappa value, and later on you can just inverse, and you will get the thickness. This is the depletion potential expression, and these are the limitation. If you are getting the value of H between 0 to 2 delta, you have to use this expression. Of if the value of H is less than 0, so depletion potential will be infinity. And if you are getting the H value is greater than 2 delta, so there will be no depletion potential. And overlap volume for spherical particles you can calculate by this formula. These are the different geometries. On the basis of the geometry, you can use the particular formula, and you can calculate the energy or and the force of interaction, basically the van der Waal interactions. So you should remember these formulas. And the calculation of depletion potential I have already indicated, but here another term, that is sigma. Okay, sigma is basically the radius of spherical particles. So you should keep in mind these conditions and apply the formula. Okay, yeah. And finally, the zeta potential calculations. This is the electrophoretic mobility. This is the constant value. Okay, and this is zeta potential here, and the relative permittivity and the vacuum, relative permittivity and the vacuum permittivity, and this is the viscosity. Okay, but for Debye-Hückel approximation, you have to use the constant value is 2 by 3. Okay, my pen is not working. And if you have this condition, that is the Kr less than zero point 0.1, okay, And the second model is the Helmholtz Smoluchowski approximation. You have to keep the value of c equal to 1 if you are having this condition uh, to be satisfied in your particular program. Okay. So these are the basic formulas, and after that I will discuss some. I will be discussing some problem. Okay, so here the spherical particles are given, which are having this 0.40 micron diameter, or you can see the radius is 0.20 into 10 raised to minus 6 meter. Okay, these particles are functionalized with carboxyl group. If the number of carboxyl group per particle is 2.3, if I denote it by n number of particle, that is the 2.3 into 10 raised to 5. Okay, calculate the surface charge density. Okay, the carboxyl group, how it dissociates. It dissociate like this. So this is the charge of one electron. So what you can do is the surface charge density, number of charge multiply by number of functional groups multiply by the charge, that is E, or divide by area. Okay, so the E value is 1.6 into 10 raised to minus 19, and the area will be 4 pi r square for spherical particles. You can calculate easily. Okay, the second is the similar. You have to consider spherical particles of different radius, and okay, calculate ratio of surface area. You have to calculate just 4 pi r1 square, r1 square, and divide by 4 pi r2 square. It will terms will be cancelled out. Okay, and what you can do, just put these values here and here. You can easily calculate the ratio, and the ratio of specific surface area. Okay, that is the area per mass. Okay, so a1 by m1 multiply by m2 by a2. Okay, so area you can write 4 pi r square, and mass you can expand it into volume into density. Okay, here you can write root of 1 v2 divided by 8. Okay, so in the particular question, the particles are having same density, so these terms will be cancelled out, rho 1 and rho 2. Rest of the question you can solve it as you want. Okay, so from the dynamic light scattering technique, diffusion coefficient you have to calculate. Oh, sorry, diffusion coefficient is given to you. You have to calculate the radius of the particle. The Boltzmann constant is also given. Report your value in nanometer. So the Boltzmann constant value you have the value of temperature 6 pi. These are the constant, and mu is the viscosity already given here. You have to calculate the radius, and the diffusion coefficient is already given. Okay. Next is the following table provides parameters that are necessary to calculate the magnitudes of Debye, Gisem, and London interactions that contribute the overall van der Waals interaction between toluene molecules. Okay, you have to calculate Debye at this separation distance and report your answer in joules. Okay, so the mu value is given here, that is zero point 0.3 dB. You can convert it into coulomb meter. Okay, and the alpha divided by 4 pi epsilon value is also given, so you can calculate the alpha value from there, and the beta value is already given, so you can arrange that value to get the final value to be used in the formula. So this is the formula for Debye interactions. Okay, that is 2 alpha mu square, that is 4 pi epsilon x power 6. Okay, you are having the alpha value, this alpha value, this mu value you are already having, the epsilon naught value you are already having, the separation distance value, that is the 4.4 nanometer. You can easily put the values, and you will get the Debye interaction contribution. Similarly, for key-sum interactions, you can put the formula, that is the 2 mu naught power 4 divided by 3 kBt, or divide by 4 pi epsilon square beta 1. You are already having these values. Okay, you just put the value and you will get answer. Okay, this is the solution. Okay, so the mu value is put here and kbt value is already put, and the separation distance is given zero point 0.4 nanometer. So here you have to put the zero point 0.4 into 10 to the power minus 9 to convert it to meter, and after that you easily solve, you will get the key sum interaction. And for London dispersion at zero point 0.4 nanometer separation distance. Okay, okay. Uh, all the three terms you have to calculate at zero point 0.4 nanometer separation distance. So you can you can easily use this expression, that is phi t plus phi k plus phi l, it's equal to 1. You are having these two values already, but what you have to do here, the suppression distance and the beta value, you have to uh, put it here, and you will get the value of this London dispersion. And you have to calculate the total van der Waal interaction at zero point 0.4 nanometer separation distance. So you can easily calculate like this. I have already explained these problems in detail in my previous sessions. Okay, so you can see the solution there. Okay, this is the another problem that is basically related to the dynamic light scattering experiment. So here, what is given to you, it is the autocorrelation function is given here. You are already provided the viscosity value, density value. Okay, and S is the magnitude of a scattering vector, and T is the delay time. You have to assume the particle to be spherical in shape, and the instrument in Segert relation to be equal to 1. Basically, Segert relations, what is the Segert relation? This is the Segert relation, and this is the constant. You have to consider it as 1. Okay, so after putting it 1, what you can do, just rearrange the formula and you will get the value of g1. Okay, and after you will get the respective g1 values from here, you can easily plot the graph between g1 st and the s square t, and you will get the value of diffusion coefficient directly, because that is the okay, so this is the a value, and e power minus d s square t, or x is basically t here. Okay, so you will get we're getting the d s square value. Okay, and directly you can uh, diffusion coefficient value you can put here. Okay. Sorry. So the x value is on x axis. You have to put these value. That is the x s square t. Okay. So x equal to the s square t value. So this value will be of diffusion coefficient, that is mentioned here. Okay. 0.288. Okay. On 10 raised to minus 10 from here. Based on the above data, you have to calculate the hydrodynamic gradients. You can easily apply the Stokes-Einstein equation, and you will get the radius of the particle in nanometers. Okay, yeah, 6 point. Okay. Next question is related to the Hamaker constant, the concept of a negative Hamaker constant. Basically, what is given here, uh, you are given the different dispersed phase. Okay, and uh, the value of Hamaker constant can be used to explain the particular engulfment by an advancing solidification front. Okay. So the solidification front takes place by when the liquid medium is allowed to solidify by subjecting to a dispersion to a thermal gradient. Okay, so a laboratory experiment is performed, and by considering liquid naphthalene dispersed with polystyrene, these are the different dispersion medium. Okay, and the liquid naphthalene is solidified, and it is required to find the dispersed particles are engulfed or rejected. Okay, and the surface tension of the solid naphthalene is denoted by 1, and liquid is denoted. Basically what you have to do is you have to expand this Hamaker constant term, that is the A321, like this. Okay, this psi 3 and sorry, gamma 3 and the gamma 1 value is already given here, and gamma 2, I think the table is missing from this question. Okay, don't worry, you can see in the particular session. Okay, the gamma 2 values are given here for different dispersion medium. So resultant, uh, the sign of the resultant Hamaker constant you can see, and based on that sign you can see whether there is a particle engulfment or uh, rejection. Okay, if you are getting the negative value, it will be particle engulfment, that is E, or this is R basically. Okay, or if you are having a positive value, then it will be the rejection. These are some flocculation phenomena or particle stabilization phenomena you can read, or you can revise again. Okay, similarly the Bayesian flocculation and steric stabilization, you have to just focus on the polymer concentration here. Okay, whether it is low concentration or medium or high. Again, this is not problem 3. Okay, and these the polystyrene particles are purchased from the supplier to see electrostatic interaction in solutions, and following are the data supplied by the manufacturer. Okay, given that the number of sulfate groups on the surface of a single particle is this, you have to calculate the surface charge density. Okay, what you for calculating surface charge density, you are having the number of sulfate groups already. You are having the charge value, that is 1.6 into 10 to the power minus 19, and divided by the area, that will be this. For a spherical particle, it will be 4 pi r square. Okay, and you can easily put those values, and you will get the surface charge density in microgram per centimeter square. You have to just convert the units after getting the resultant value. Okay, so uh, make sure that you are getting the value in microgram per centimeter square. The second part is you have to calculate area per sulfate group in angstrom square. So what you will do, that is whatever area you will be getting, you have to divide that area by number of sulfate groups. Okay, you will getting the area per sulfate group in angstrom square. Basically, first you will getting the meter or centimeter, and after that you can convert in the angstrom square. Okay. Again, the next problem is uh, okay. Consider a charged surface with a surface charge density, and the surface is this, and these the data is given here. Okay. Use the capacitor rearrangement to model the electrical development. So calculate the strength of the electric field. So you can easily apply this formula. That is E is equal to sigma star divided by sigma epsilon r epsilon naught. Okay. This is the surface density. Number of surface charge density is directly given here. That is 6.9 into 10 raised to minus 2. Okay. Put those values, and you will get the strength of the electric field. And the calculate the gradient of the surface potential. Okay. You have to calculate the del psi basically. Okay. So the thickness is given here. That is delta. Okay, but okay. So del psi is equal to this E electrical potential into psi. Okay, For e value you can okay, so from here you can calculate the e value and multiply by this, that this is the 4.4 nanometer, that is double layer thickness. So we'll get, you will get the value in of the potential, and later on you can convert it into millivolt. Okay, the most frequent question, like this, you have already observed in my sessions. Okay, so on the surface of a certain material, there is one ionized group per this surface area. Okay, this surface is immersed in an aqueous solution containing this electrolyte, that is of the 10 millimolar NaCl, and these are the standard values you have given here, and this is the important hint. You have to assume the low potential limit, and on the basis of this data, you can calculate the screening length and the surface potential in volts. Okay. First, what you have to do is this, convert this millimolar into molar, and after that, okay, and for similarly for surface area, that is 4 nanometer, convert into meter square, and you know the formula for k square, that is e square by epsilon kbt, and summation of n zi square. So you have to reverse that formula, you will get this expression. Okay. Except these standard values, what you have to calculate, that is the n value, n infinity value. Okay, using this simple formula. Okay, and the molar concentration here 1000 and this. Okay, so you will get the number density at infinity. Okay, after that what you have to do is this is the charge. Okay, if you are having NaCl, so Na positive, Cl negative, this is minus 1 square. So after that you will sum the expression, or you will get the final value, and put that final value here. You will you will getting the value in meter. Okay, and convert into the nanometer. You will getting the dBA length, that is the k units. Okay. Similarly, surface potential. Okay, and you can use capacitor model, because they can converge. Okay, so based on this formula, you can calculate the surface density. You can apply the capacitor model formula, and after that, you can put the value of k inverse in place of delta. So you will getting this potential value. Okay. Similar problem is here, but you have to calculate the molarity of sodium chloride upon mixing and sodium sulfide upon mixing. Okay, so you can just calculate by simple applying the dilution factor. Okay, let's say if you are having the concentration of 0.01 molar sodium chloride. Okay, so molarity of NaCl will be 0.01 into its volume, that is the 400 ml, divided by total volume, that is 600 plus 400, that will be 1000. Okay, so this will be the final concentration of NaCl. Similarly for Na2SO4. Okay, after that what you have to calculate the number density for sodium chloride and sodium sulfate individually, and total value you will get by adding the number density, or you can calculate the summation for individual, and later on you can add those two values like this. Okay, so this is the final value of this term, and simply you can calculate the dBA length by applying this formula and putting that value here. Okay, an approximate expression is given here for the repulsive potential energy due to electrical double layer overlap versus the surface distance, that is S. Okay, and these are the standard values, and K is the inverse device screening length. Basically, this is the inverse device screening length. Okay, that is the K inverse 1, that is K. Okay. particles have a part surface potential of 25 millivolt, that is psi naught, and immersed in water. This is the concentration of electrolyte given here. Assume that the presence of salt does not affect the dielectric constant of the medium, the diameter of the spherical particles in 100 nanometer. You have to calculate the inverse Debye screening length, that is K value, the strength of electrical double layer at 3 nanometer, 6 nanometer, and 9 nanometer. Okay, so okay, so use the as usual, use this formula, and you will getting the value of the inverse Debye screening length or kappa value in meter inverse. Okay. But for calculating the strength of electrical double layer, okay, what you have to do, you have to use this particular expression, okay, that is V electrical double layer, that is pi epsilon d, and epsilon naught square. You are already given here, that is the psi naught value here. D is the basically the diameter, I think. Diameter is already given here, and you can simply calculate for 3 nanometer, for 6 nanometer, and for 9 nanometer. You can calculate, or I think for yes, for 9 nanometer, you can easily calculate, or you can use this alternative formula, that is this one. You have to simply take the ratio of V electrical double layer overlap at 6 and 3, and you calculate one of those, because you are already having the value at 3 nanometer. Okay, but you have to calculate the potential value in terms of kBt, so you have to simply divide by the resultant by kBt, that is the 1 point the value of Boltzmann constant, that is 1.38 into 10 is to minus 23, and the temperature that is already given in the question. Okay, and the discussion forum question I have already discussed two times. Okay, what you have to do here, you have to uh, first you have to see there is symmetric electrolyte or asymmetric electrolyte. Based on that, you have to calculate the concentration of different ions. If you are not having the formula of asymmetric electrolyte, based on this ratio, z positive to z negative ratio, you have to construct the molecular formula, and after that you have to note the concentration of the individual ions. And in the similar manner, you have to calculate this number density, and based on that you can calculate the kappa value, or whatever the question is demanding. You can calculate the electrical double layer thickness. And this is the final question of this session. What is the zeta potential of a particle that displays the mobility of 10 s to minus 4 centimeter square per volt second in liquid? Basically, this is the u value given here, and the viscosity eta. This is the eta value, and the relative permittivity, that is epsilon r. Assume that the applicability of Debye-Huckel approximation epsilon naught can be taken as this. Report your answer in millivolts. So what you have to do is the electrophoretic mobility, that is U is equal to C, the zeta potential epsilon r epsilon naught divided by eta. Okay. So C value will be 2 by 3 for Debye-Huckel approximation. This value you are already having, and these two values already given in the question. This value is already given in the question. You can easily calculate the zeta potential value. Okay, after that, converting, if you are getting the value in volt, uh, remember to convert into millivolt. Okay. Oh, and this is the second question of discussion forum. Somebody has posted it. I have already solved that problem in any any of the sessions. I don't remember. But what you have to do is the kappa value you can easily calculate. You have to calculate the surface charge in coulomb. Okay, this is the surface charge expression given here in this question. You can put those values and you can get the surface charge. Okay, after that you have to calculate the surface charge density. Okay, so you are having the surface charge, divide by the area. That is area. I think here you can use the spherical particles. Okay, so you can put the 4 pi r square and r value is given here. Okay, calculate the number of charged surface on the particle surface, charge groups, sorry. Okay, so you have a total charge value from this question. Just divide the value by 1.6 into 10 is to minus 19, because only the dissociated or charged groups are having this value, because one electron equal to 1.6 into 10 raised to minus 19. If you divide the total charge by this value, you will get the number of charge groups on the particle surface. Okay, if you assume that only 20% of the molecule on the surface of missile are dissociated, this value you are getting, this will be equivalent to 20%. Okay, what you have to do is you have to calculate the aggregation number, or aggregation number, what is the number of surfactant molecules in a single micelle. Okay, this single micelle, that is you have to calculate the total number. So you can easily back calculate, that is let's say this number is x, so x multiplied by 100 divided by 20, you will get the aggregation number. Okay, so this was the last question for this particular session. Okay, I think I have included most of the formulas in this particular session, and you can easily solve these expressions. I have tried my best to incorporate all the things in this particular sessions for your revision. Okay, uh, so thank you, and good luck for your exams. Thanks a lot.